All right, good day, one and all. This video is being made to explain organic chemistry as taught by Professor Upon Chichiku. This material is being made by the GPSA Academic Board. Then, point of caution, this video is a supplementary material, not an alternative material. And then, if you have any issue, you can kindly see any member of the GPSA Academic Board. And then if you want extra private support, you can also contact the number that I would give at the end of the class. So without much ado, I will start. All right, so today's lesson will be focused on alkanes and cycloalkanes, right? So that's all we'll talk about. But before we delve into alkanes and cycloalkanes, we have some little introduction that will help us understand what we are doing better. The first thing we'll talk about is hydrocarbons. Now, as the name implies, hydrocarbon contains carbon and hydrogen only. Carbon and hydrogen only, very important, right? Good. Now we are saying that we have two main classes of hydrocarbons. We have aliphatic and aromatic, right? Now aromatic will be discussed in a different lesson. So what we are focused on, or what we would pay attention to, is aliphatic. Now hydrocarbon, which is open chain. So all open chain hydrocarbons are aliphatic hydrocarbons. Yes. But then there are ring hydrocarbons which are also aliphatic, right? But then all aromatic hydrocarbons are ring structures. Now this shouldn't confuse us. What we are saying is that if we have, let's say, a chain like this is an unbranched chain. If you have a chain like this can be an organic compound. So this is a branch chain, right? Now once it's an open chain like this, right? Good. It is aliphatic. Now we can have some as a ring. Now you can see that if it's a ring, right, the ring can be aliphatic or aromatic, right? But before you can be aromatic, you should be a ring. So there's no way you can get an open chain like this, right, which will be aromatic. No, under our studies. Good. So that's what we are saying. So the aliphatic that we are focusing on, we are not talking about aromatic today, but aliphatic we are focusing on can be either open chain. The open chain can be unbranched, as we have here. That is something like this. This is unbranched. Then this one is branched. So we have this one is branched, right? So this is branched. Good. So it can be unbranched, it can be branched, or it can be cyclic. Right, so example of cyclic one is the cycloalkane that we will talk about today. Now, all these skeletal structures, we will learn them, so we don't have to worry our head with them. Good. Now, the next thing we are saying is that aliphatic hydrocarbons include three main groups. We have alkanes, alkenes, and alkynes. Now, we'll talk about alkenes and alkynes in different lessons. So the focus here is alkanes. Now, we have been fortunate to have examples of alkanes, alkenes, and alkynes. Now, we should take note of these ones, even though they will become very familiar with time, right? So this is ethane. Now, it has only single bonds. That's to say, it is fully saturated, and that is typical of alkanes, right? Now, this is ethylene. That's an alkene, right? Good. Now, this is the common name. The systematic name is ethene. It's ethene, sorry. Ethene, right? Now it has double bond, carbon-carbon double bond, which is typical of alkenes, right? And the last one is acetylene. And acetylene has carbon-carbon triple bond. Acetylene here is the common name. The actual name is ethine, right? This is a systematic name, ethine. Right, and then the carbon triple bond here is typical of alkynes. Good. Now they have also given us an example of an aromatic hydrocarbon, also called arenes. And then the example here is benzene. Benzene is the parent aromatic hydrocarbon. Parent aromatic hydrocarbon. Now we didn't talk about this, so let's just go on. Good. Now, aside talking about hydrocarbons, the next thing that we have to focus on are functional group. So what is a functional group? Now we are saying a functional group is the structural unit responsible for the reactivity of a given molecule under a particular set of conditions. Now, if I'm supposed to break this down, the first thing you have to keep in mind is that always reactions will occur under a particular set of conditions. And then if these conditions are not met, reactions will not occur. So this part of the definition is very important because always before a molecule undergo a reaction, it means you have subjected it to a particular set of conditions, right? Good. Now, that's not the focus. The focus is that the functional group becomes the structural part, the structural unit within the whole molecule that is responsible for its reactivity. So, assuming we are talking about, let me use these structures as examples. Now, we have alkenes, right? Now, what is the reaction that alkenes will undergo? Alkenes undergo substitution reaction. It simply means you are removing something and then you are bringing another thing. So what happens here is that we remove any of the hydrogens here. Now, when any of the hydrogens here is removed, another atom or group of atoms will replace this hydrogen. So what is responsible for the reactivity of alkenes here is the hydrogen. And so the functional group in the alkene is just the hydrogen. That is what we are talking about. So the hydrogen here is the functional group because it's the hydrogen that will be removed for an atom or group of atoms to be introduced. Does it make sense? The next thing is, let's use the next structure, alkene. Now, what is the reaction that alkenes will undergo? Alkenes will undergo addition reaction. Now, where does this addition reaction happen? Addition reaction means we are breaking this unsaturation. So the whole thing is around the C, double bond C. The pi bond in this one is what is broken. And so the functional group in the alkene is this one, the C, double bond C. If I come here, the alkyne, the functional group in the alkyne is the C triple bond C because it will typically undergo addition reaction. And the addition will occur here, where we have the triple bond, where we have the unsaturation. And so this structural part, this unit of the whole molecule is the functional group because it is the part or the unit which is responsible for the reactivity of the whole compound. Does it make sense? So that's what we are talking about when we talk about a functional group. Now, we are also saying that it can be as small as a single hydrogen or several atoms. It can also be very large. Now, we are saying a hydrogen is hydrogen atom is the functional group in alkenes. Now we are saying key functional groups in organic chemistry include alcohols, alkyl halides, amines, epoxides, ether, nitro alkenes, thiols, carbonyls, and arenes. Now, carbonyl containing compound ranks amongst the most abundant. This is general information for you, right? And then biologically important class of naturally occurring substances. Now we are seeing that the carbonyls, right, it's not just a single class. It also contains subclasses like aldehydes, ketones, carboxylic acid, and carboxylic acid derivatives. Examples of the carboxylic acid derivatives are acyl halide, acid anhydride, esters, and amides. Very simple. Good. Now let's come to alkenes. Now we are saying alkenes have general formula of CnH2n+2. Now, this means that before you can be an alkene, you should obey this rule. That is the simple meaning of this, right? Now, the N here are integral numbers, right? So integral values from 1 onwards. So it can be 1, it can be 2, it can be 3, right? So assuming N is equal to 1, right? If N is equal to 1, then I have C1H2 into brackets 1 plus 2. right? And that will be CH4. This is an alkane, methane. N can be equal to 2, N can be equal to 3, N can be equal to 4. So it goes on and on and on, right? Now we are saying the primary source of alkane is petroleum. Now we are saying the simplest and most abundant alkene is methane. Now methane is the most abundant because it is the most stable. Let's keep this in mind. That is the main reason. The main reason why methane is the most abundant alkene is because it is the most stable alkene. Now, what makes it the most stable alkene is explained down here. So let's quickly go there and then explain. Now, the first three basic alkenes that we'll talk about are methane, ethane, and propane, right? Good. Now, you realize that the carbon atom here, the central atom here, is sp3 hybridized. Now, the sp3 hybridized orbital, right, should have a bond angle of 109.5. Good. 109.5. Now you realize that the methane has bond angle of exactly 109.5 degrees. But then if you go to the ethane, the bond deviates. It deviates to 111 degrees. And then if you go to propane, it also deviates to 112. And so it shows that as you are moving along, there is deviation because of repulsion, right? There is deviation in what? In the bond angle. And so it is only methane that will fit perfectly. Methane has the right bond angle and then the right bond length to fit perfectly into the tetrahedral structure of the hybrid orbitals. Now, because it has that perfect bond angle and perfect bond length, right? It is the most stable because it fits perfectly into the tetrahedral structure. The others, because of their deviation, you realize that the bond length deviates and then the bond angle deviates. So they don't really fit perfectly. And so the stability would decrease. So I'm saying that methane is the most abundant because it is the most stable. Now it is the most stable because it has the right bond length and then bond angle to fit perfectly into the tetrahedral structure of the hybrid orbitals of the central carbon atom here. Very simple. So that is that for that. That is that for that. Good. Now let's continue. We are also saying that ethane and propane are second and third most abundant. So as we go along, the deviation increases, right? Good. So methane is more stable, followed by ethane, and then propane. Because as you move along, you realize that the deviation also becomes bigger. So your stability becomes smaller, and then the abundance will start decreasing, right? Good. Now we are saying in natural gas, methane is 75% approximately, ethane is 10% approximately, and propane is 5%. So this is just numbers to show abundance, right? Good. Next one. LPG is mainly propane-rich mixture of hydrocarbons liquefied under high pressure. Now, this statement will also show that in LPG, it might not be only propane, but among all these three abundant gases, propane is the highest because it is mainly propane rich. The next question will be, why is it that in LPG, it is propane rich or the propane proportion is higher? Why isn't methane higher? Now, the idea is that we want to liquefy the gas. Propane, methane, and then ethane are all gases, right? Now, in an attempt to liquefy it, we consider how strong their intermolecular forces. Now, propane, ethane, and methane, they are all nonpolar compounds. Now, they are nonpolar, and so the intermolecular force between them is the weak van der Waals force. Weak van der Waals force, or you can say the induced dipole force, right? So the weak van der Waals force. So weak van der Waals force. Now, this weak van der Waals force is favored by larger surface area and higher molecular mass. So you realize that between methane, ethane, and propane, propane has the highest molecular mass. It also has the highest surface area. Now, because it has the highest molar mass and then it also has the highest surface area, it will have the highest intermolecular force of attraction. And so it is easier for you to liquefy the propane relative to the methane and then what? The ethane. That is why it is the highest in LPG, because LPG is, we are liquefying the gas, we are turning the gas to liquid. Now, if you want to turn the gas to liquid, we want the one that can be easily liquefied. And then between the three, it is easier for you to liquefy propane because it has what? It has the highest intermolecular force. Now, why does it have the highest intermolecular force? It has the highest intermolecular force because it has the highest molar mass and then the highest surface area among the three most abundant gases. Right? Is that clear? Good. So that is that for that. That is that for that. Good. So shape of the alkanes. Alkanes are supposed to be tetrahedral, right? Tetrahedral. You have only sigma bonds. You have only sigma bonds. The carbons there are sp3 hybridized. These are properties that we should never forget. So they are sp3 hybridized. Of course, they are tetrahedral shape, right? Good. That is that for that. Good. Nomenclature of alkenes. So we are saying that nomenclature in organic chemistry is of two common types. We have the common or the trivial names, and then we have the systematic names, right? Good. Now, the common names are sometimes used. So you have, in as much as you are learning the systematic names, make sure you also know the common names. If I say acetylene, I expect you to know acetylene, right? Good. So you learn both of them hand in hand. Good. Now the next statement is saying that the number of carbon atoms in an unbranching alkane precedes the suffix "ane." So if it's one, right now we are talking about unbranched, so there's no substituents. That's what we are saying, right? So if the carbon atom is one, we call it methane. If it's two, it's ethane. If it's three, it's propane. If it's four, it's butane. So it goes on and on and on. Now we have to master almost everything here, right? The first to 10 is common. I mean, first to 10 is common, but then you have to know 20. So 20 is icosane, cosine. You have to know 30. You have to know, so roughly know all the names, because there are bonus questions that will come and then they will ask you to name this organic compound, C20H42. Now, this is a bonus. If you know, you know. If you don't know, you can't guess it. So you should learn it, right? That is all for the unbranching. Now, the description becomes a little bit complex, if we have a branching. So now we have to name substituents. We have to name substituents. Now, there are some rules that we'll go through step by step to know how to name substituents. So the first one, the parent of the alkene is the longest chain of the carbon. So the longest chain is the parent, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you realize that the one that has been highlighted here, right? This make up the longest chain. So that will be the parent. So the longest chain here has 6 carbons, and then the parent name for this one will be hexane, right? So hexane will be the parent name. Now, it doesn't mean that is the full name. That will just be the parent name, right? So always we check for the one that has the check for the longest chain. Very simple. Very simple. Good. Now, in this example, we have to still check for the longest chain. So the numbering can be here. So I think obviously you see this is the longest chain, right? Good. So 1, 2, 3, 4, 5, 6, 7. So it means the parent's name will be heptane, right? The parent chain will be heptane. So that's the one that has been highlighted in blue. And that's the only rule we have spoken about. We'll talk about the others as we go on. Now, the second rule we are considering says that begin with the end of the chain nearer to the substituent. Number the longest chain. So after finding the longest chain, then see you can start numbering from here. So this is the longest chain, right? Now you can start numbering from here or you can start numbering from here. Now what we are saying is that choose a starting point such that the numbering will be closest to where there's substitution. So then instead of naming it 1, 2, 3, 4, 5, 6, such that this substituent will be on the 5th carbon, we will turn it from the other way around and then start numbering from here 1, 2, 3, 4, 5, 6, such that the substituent can be on the carbon number 2. So always we want to give the substituent, right, the least number. We want to give the substituent the least number. Very simple. Now that's the same thing that has been done here. We numbered from down here in order to give the substituent a small number, which is 3, right? Good. Now the next rule. So the next rule says that we should use the numbers obtained by application of rule 2 to designate the location of the substituent group. So now I realize that the parent name is always gotten from the longest chain. So because the longest chain here it says carbons is hexene, right? Now we are saying we should use the number we have gotten to indicate the location of the substituent and name it. So now I realize that this substituent, which is the methyl group, right, is on the 2nd carbon. So we'll have 2 methyl hexane. Now this group here is called methyl because it is 1 carbon, right? 1 carbon, if it was a full compound, would have been methane. Now, because the substituent, we remove the A and E and put Ly there. So instead of writing something like methane, when it's a compound, if it's a substituent, we write something like methyl. That is, we removing the last 3 and putting Ly there, showing that it is what a substituent. And so here we'll have 2 methyl hexane. Now the longest chain here is 7 carbons with heptane. And then the methyl group, which is a substituent, occurs on the 3rd carbon in the longest chain. So we'll have 3 methyl heptane. Very simple. Very simple. Let's move on. So the next rule now is telling us that when 2 or more substituents are present, give each substituent a number corresponding to its location on the longest chain. The substituent groups are listed alphabetically. Good. So I think this one is better. We use an example to explain, right? So let me demonstrate how we came about this name here. Now we have to check for the longest chain. If I count from here, 1, 2, 3, 4, 5, 6. Okay. Now I can also count from here 1, 2, 3, 4, 5, 6. So 6 going up here. Now this is a very simple one. There are other rules to explain how to go about when you have 2 chains like this, right? But let's just number it like this. So we have 1, 2, 3, 4, 5, 6. Good. Now you realize that I have substitution. Okay, let me number it in a reverse way and show you why I chose to number it this way. So 1, 2, 3, 4, 5, 6. Now if I number it as I've done in the black ink, I'll have substitution on number 2 and substitution on number 4, right? 2 plus 4 is 6. Now, if I number it in the reverse as has been done in the red ink, you realize I have substitution on number 3 and a substitution on number 5. That is 8. Now, always you number such that the substituent will have the least sum. And so it means that I cannot choose the 8. That means I cannot work with the one in the red ink. I have to work with the one in the black ink because that gives me the least number, right? So that is what I'll consider. That's the one I'll consider. Now I realize that on position 2, I have a methyl group there. And then on position 4, I have an ethyl group, ethyl from ethane, 2 carbons, right? I have an ethyl group here. Good. And so it means I have 2 methyl, I have 4 ethyl. Now they are saying that's methyl and ethyl. I should arrange them in alphabetical order. So then I ask myself, if I'm reading my ABCD, which of the letters here come first? Is it M or E? Obviously, it is E. So then I'll have 4 ethyl, 2 methyl, and then the parent, which is this carbons here, will be hexane. So that is what we have here. Very simple. Very simple, right? Good. Now, there's one thing we have to note here, that between a number and a letter, we put dash. So this dash between a number and a letter. And then between 2 numbers, let's say if you have 2, 4, we put a comma. Very important rule. So if we are writing 2 numbers, you put a comma there. If you are writing, that's if there's a junction between a number and a letter, you put a dash. Very important. Very important. Good. Now, the next rule is saying that when 2 or more substituents are identical, right? Okay, let me solve this one before I move on. So, I would have 1, 2, 3, 4, 5. Right? I'll not name it the other way around. 1, 2, 3, 4, 5. Because if I do it like as I've done in the red ink, the substitution will be on position 3 plus position 4. And that will be 7. But then if I number it like this, as I've done in the red ink, the substitution will be on position 2 and 3, which is 5. Right? So I would always prefer the red. I would prefer the red, numbering such that I would have the least sum. So now, if I have 5 total carbons, that means the parent's name is what? The parent's name is pentane, right? Now, on position 3, I have a methyl group. On position 2, I have a chloro group, right? Yes. Now, we ask ourselves between methyl and then chloro, which one comes first if I'm naming my ABC, my alphabet, right? C comes before M. So I will have the 2 chloro and 3 methyl. And always remember between a number and a letter, we put a dash, right? Very simple. So I would have 2 chloro, and 3 methyl, pentane. That is that for that. That is that for that. Good. Let's move on. So moving on, the next rule, when 2 or more substituents are identical, indicate this by the prefix di, tri, or tetra. Di, tri, or tetra. So di is when there are 2, tri is when there are 3, tetra is when there are 4, right? And penta, it goes on and on and on like that. So let's consider these examples. Let me work them out. So I would have 1, 2, 3, 4, right? Now I realize that because it's 4 carbons, I'll have butane. Now, on position 2 and 3, I have the same groups that have methane and methane. So I would have 2, 3 dimethyl butane, right? If I'm trying this one, this is 1, 2, 3, 4, 5, right? Now on position 2, I have a methyl group. Position 3, I have a methyl group. Position 4, I have a methyl group. So I'll have 2, 3, 4 trimethyl pentane. Remember, between numbers we put commas, right? So between numbers we put commas. Now, if you come here, the longest chain 1, 2, 3, 4, 5. So I have pentane, right? Now on position 2, I have 2 methyl groups. on position 4, I have 2 methyl groups. So I'll have 2,2, right? 2,2,4,4 tetramethyl pentane. Very simple. That is that for that. Good. Now we are still on nomenclature. The next two, we are saying that when two chains of equal length compete for selection as parent chain, choose the one with the greater number of substituents. So this is a very important rule that will save you in times of some difficult or tough examples. So we have this one. You realize that if you number like this, 1, 2, 3, 4, 5, 6, 7, right? You have 7. Now you can also decide to number like this. So 1, 2, 3, 4, 5, 6, 7, right? Now in that case, you realize that you are getting 7. So the same longest chain. Now someone else might also decide to number like this. 1, 2, 3, 4, 5, 6, 7. So you realize that there are 3 different ways of what numbering. Now let's consider them one after the other. If I consider the red one, the one in red ink. Now, if I take that chain, how many substituents would I have? I have a substitution on position 3, another one on position 4, another one on position 5, another one on position 6. So I'll have 4 different substitutions. Now, if I take the one in the green ink, how many substitutions would I have? I have substitution on position 2, substitution on position 3, and then substitution on what? On position 4, because this will be the substitution now, right? So I'll just have 3 substitutions. Now, if I take the one in black ink, I would have substitution on just this one. This will be the only substitution I'll have, right? So just this one. So I'll just have 1 substitution. Now, this rule is saying that if the chain lengths are equal from different ends, make sure you choose the one with the most substituents. It means we have to go in for the one that is in the red ink. That's the numbering we have to choose. So let's clean the others and then choose that one and work with that one. Right, good. So that is what we have to work with. Now, after getting our longest chain, the next thing that we have to do is to name the substituent. So we have 3 methyl, 5 methyl, and then 6 methyl. So, and then we have this propyl here, 4 propyl here. So alphabetically, M, the methyl here, comes before the propane. Now you still contain the methyl, not the tri. Contain them, you consider the methyl, right? So the methyl groups come before propane, P, M comes before P in the alphabetical order, right? So we would have 2. Oh, okay. So there's one last thing that's one last rule that I have not considered. Now that rule is we have to also name such that we give the smallest numbers to substituents. So in the same red ink, I'm supposed to number from here. 1, 2, 3, 4, 5, 6, 7. Now I realize I'll have substitution on, that's if I'm considering this side, I have substitution on position 3, position 4, position 5, and position 6. Now, if I add these numbers, this one will give me 11, this is 15, this is 18, right? Now, if I consider this direction, that's numbering to this direction, I'll have substitution on position 2, position 3, position 4, and position 5. Adding this is 9, 9 plus 3 is 12, 12 plus 2 is 14. Right, so 14. It means I have to choose the one that goes to this direction instead, right? That means I have to clean my first numbering. Good. So you have to remember every single rule, else you get an answer, but that will not be the right answer. So after numbering here, I would have 2-methyl, 2-methyl, there's 3-methyl, and then there's 5-methyl. So 2, 3, 5 trimethyl, 4-propyl heptane, because we have 7 carbons in the parent chain. Very simple. Very simple. Good. Good. Now we are still on nomenclature. The next rule. So we are saying when branching first occurs at equal distance from either ends of the longest chain, choose the one that gives the lowest number at the first point of difference. Good. So now you realize that if I number from here, 1, 2, 3. Okay, let me 1, 2, 3, 4, 5, 6. Good. Now you can use the same formal rule. You can also number from here 1, 2, 3, 4, 5, 6. Right. Now the substitutions for this one, that's if I'm counting to this direction, will be on 2, 4, and 5. Now 2 plus 4 is 6. 6 plus 5 is 11. So here. Now, if I'm numbering to this direction, substitutions will be on 5, 3, and 2. Now, 5 plus 3 is 8. 8 plus 3 is 10. So 10. So you realize that numbering to this side is the better one. So that's what we'll consider. So we'll have 2, 3, 5 trimethylhexane. Right? That is the next rule. Very simple. Very simple. And we have been applying this already. So there's no issue with this one. With this one. With this one. With this one. Good. Now that's an easy way of explaining this, but then there are other complicated ways of doing it. So nomenclature, still on nomenclature of branch ones. Now we are coming to talk when we have a situation where we have a substituent on a substituent, right? Substituent on a substituent, that is the concept we are introducing ourselves to here. Good. So assuming we have 3 carbons as substituents. Now that 3 carbon can be in a straight chain, not straight, but let's say on branching. Now, if it's not branch, call it propyl, right? 3 carbons, propane, propyl. Good. But then if it is branched, so now in this picture here, that means there's a long chain attached to this one, right? Now the 3 carbons which are acting as substituents are not in an unbranched chain, it is branched. So what we do is that from the point of attachment, we start numbering 1, 2. The numbering can also go here. We still focus on the longest chain. If I number here, it will still be 2. So, I mean, there's no difference, right? So, I just go with my first numbering. Go to 1, 2. Now, that 1, 2, the longest chain that I've gotten will give me ethyl, right? That's ethyl. That's 18, 2 carbons. Now, on that ethyl, that first carbon, numbered carbon 1, has a methane group here. It has a methyl group, sorry. It has a methyl group here. And so I have a substituent on this whole substituent. Now that substituent occurs on carbon 1. So I would have 1 methyl. That is this one, the substituent. Ethyl, that is the whole of the substituent, right? So 1 methyl ethyl, 1 methyl ethyl, and the parent name will continue, right? 1 methyl ethyl, and the parent name will continue. Now, usually we put this in brackets when we are naming. We'll see examples like that. The common name for 1 methyl ethyl is isopropyl. Now, you can also keep this. Some questions have this, you should know. But with time, you just get to know all these. So you don't have to worry your head over that, right? So 1 methyl ethyl. Now, 1 methyl ethyl, the systematic name, isopropyl is common name, right? Now, they are like numbering always begin at the point where the group is attached. So the point of attachment would always be where the naming was started. So say the long chain is here. Now this is the substituent. This is the carbon that is attached to the substituent here, And so always the numbering should start from this carbon, right? The carbon which is directly attached to the substituent. Very simple. Very simple. Good. Now 4 carbons. If we have 4 carbons, as has been illustrated here, and it's unbranched, if it's unbranched, it is butyl. If it is branched, right, then we start naming them. So this is the longest chain here. 1 is here, 2, 3. Now we can decide to number the 2 here, but then we realize that we'll have a shorter chain. We always want the longest chain. Good. So we would consider the first one that gets it 3. The 3 will give me propyl. Now on that one, the first carbon here has methyl there. So I'll have 1 methyl. So this is it. 1 methyl propyl. Now 1 methyl propyl is also known as sec-butyl. Sec-butyl, right? That's a common name. Good. Now the next one, isobutane. Isobutane. So still we are talking about 4 carbons, right? Now the compound here, as the parent compound, is isobutane. And I can act as a substituent. When it's acting as a substituent like this, we can name it. This is the parent. Now we start numbering 1, 2, 3. It's still propyl group. On the second carbon, we have a methyl group there. So then we'd have 2 methyl propyl, and that is also known as isobutyl group, right? Now this one, 1, 2. So that's the longest chain. You can decide to name 1, 2, or 1, 2. It should always start from here, the carbon which is directly bonded to the parent chain, right? Now, each of the names that we are numbering that we have done ends at 2, so we can just consider one of them. Now, after getting the parent chain 1, 2, you realize that we have ethyl. Now, on the carbon 1 of the ethyl, we have 2 methyl groups. So then I'll have 1,1-dimethyl ethyl. 1,1-dimethyl ethyl. 1,1-dimethyl ethyl. Very simple. Very simple. So that is that for that. Now we are supposed to try these examples. Okay, so let's work on the first one. Now, the first one, the longest chain, this one, I can count from here 1, 2, 3, 4, 5, 6, 7. Counting from there, it's heptene. That's the longest chain, right? If I decide to come down here, it would end at 6. So that cannot be. If I come here, it still end at 6. So that cannot be the longest chain, right? Now, the substitution is at position 4. I'll number in the reverse manner and see whether I'll still have the substitution position 4 or maybe a smaller number, because we always want the smallest number. So 1, 2, 3, 4, 5, 6, 7. Good. Now you realize the substitution is still at position 4. It means we can number it anywhere and then we'll get the same answer. Right, good. So then after comfortably settling on my this, then I realized that 7 carbons, so I have my parent name to be heptane. Heptane. Good. Now on carbon 4, I have a substituent. But that substituent is a branch substituent. So on carbon 4, if I'm counting, this is the one attached. So this can be carbon 1, and then this will be carbon 2. So then I have an ethyl group, right? Now on that ethyl group, the carbon 1 has a methyl group. So I'll have 1 methyl ethyl. Now that 1 methyl ethyl is at position 4. So I told you, always put the substituent of a substituent is put in a bracket. In a bracket. So it's at position 4. Right? So 4 into brackets, 1 methyl ethyl heptane. That will be our answer. Very simple. The next example is here. We can numbering from here would make the substituents land at 5, position 5. Numbering from here will make it land at position 4. So we'll start numbering from here. 1, 2, 3, 4, 5, 6, 7, 8. So 8 is octane. 8 is octane. Now on position 4, right? we have, this is the carbon that is attached firstly. So carbon 1, and this can be 2. So then I will have 1, 1 dimethyl ethyl. So then I'll have 4. That is this position 4. 4 into brackets 1, 1 dimethyl ethyl octane. Now 1, 1 dimethyl ethyl is the same as tet butyl. So then you can also name tet butyl. Bear in mind that tet butyl is not systematic, but it's the common name of 411 dimethyl ethyl octane. Very simple. Very simple. Next up, naming or nomenclature of the cycloalkanes. Right now, cycloalkanes are alkanes that contain a ring of 3 or more. Now, the least number of carbon that will be found in a ring are 3 carbons. 2 carbons cannot form a ring. So 3 carbons. And that's for hydrocarbon, right? Good. Now, cycloalkanes are characterized by the molecular formula CnH2n. So now there's the formula. You realize that it is different from alkenes. So they have different molecules. Even though they are both alkenes, open chain alkenes have different formula from cycloalkanes. And then I think it is at this point that I'll tell you that cycloalkanes are isometric, right? So we talk about isomer later, right? But then their isomers are alkenes. So we'll talk about isomers later. But then alkenes also have the same molecular formula, right? So if I give you any molecular formula for a cycloalkane, now I can also write that cycloalkane as an alkene, right? Structural isomers. So we'll talk about them as we go along. Very simple. Very simple. So let's name this. Now, let's look at the rules involved in naming cycloalkane. So these are examples. This is cyclohexane. It has 6 carbons. So this is cyclopropane. It has 3 carbons. So propane, but then it's cyclic. So cyclobutane, cyclopentane. Now, they are saying that cycloalkanes are named by adding prefix cyclo to the name of the unbranched alkane with the same number of carbons. So, assuming it was 3 carbons, we'd have called it propane, but because now it's a ring, call it cyclopropane. Very simple. Very simple. Now, you can also name substituents. So, this will be position 1. Because position 1, we don't write it. So, you can write methyl cyclopentane. Now, this one will number it. So, we start numbering from here. 1, 2, 3, 4, 5, 6. I'm not going the other way around because going either way or starting from here would make the substituent number big. So this is the best arrangement. You can try the other one. You realize that the substitutions here are on 1, 1, and then 3. Any other numbering would make it higher than the total here, which would be 5. Right? That's 1 plus 3, 1 plus 3. But so with the naming I would have here, I would have 1, 1 dimethyl, then I would have 3 ethyl. Alphabetically, ethyl, E comes before M. So then I would have 3 ethyl, 1, 1 dimethyl, cyclohexane. Now, the last one here has not been named, but we have to name it here. So what happens here is that this chain here is longer. It has more carbons than the ring here. So then the ring here becomes the substituent. All these ones, the chain here were shorter than the ring. So then the ring was the parent. But now the chain is longer than the ring. So the ring becomes a substituent. So if I'm numbering, I have 1, 2, 3, 4, 5. Right? Now on the second carbon, I have this substituent. This substituent, if it's a compound on its own, we call it cyclopropane. But now we'll call it cyclopropyl. Cyclopropyl. Right? And then because it's 5 carbon is pentane. So pentane. Now we are not done. What position is the cyclopropyl? It's on position 2. So I'll have 2 cyclopropylpentane. That will be the name of this compound. Very simple. Very simple. All right. So the next thing for us to do is to classify carbons and hydrogens in alkanes. Now, the carbons and hydrogens can either be primary, secondary, or tertiary. Right. So the colors here have been used to indicate. Now, primary carbon would be a carbon which is bonded to only one other carbon. Now, the hydrogens associated with that carbon would be primary hydrogens, right? So you realize that the carbon in blue here, the carbon here is bonded to just this one. So it's only bonded to one other carbon. This one is bonded to one other carbon. This one is bonded to just one other carbon, right? So these carbons are primary carbons. The hydrogens attached to them are primary hydrogens. Now, primary hydrogens usually occurs in groups of 3. That's in hydrocarbons. You realize that the primary hydrogen will occur in groups of what? 3. Good. Now, secondary carbon is bonded to 2 other carbons, right? It's bonded to 2 other carbons. So we realize that the one in green bonded to this one, it's bonded to 2 other carbons. Now, you realize that if this carbon is secondary, the hydrogens attached to it are also secondary hydrogens. The secondary hydrogens in hydrocarbons occurs in groups of 2, right? Then we have tertiary. Tertiary carbon is bonded to 3 other carbons, right? And then it has, if it has a hydrogen attached to it, that hydrogen becomes a tertiary hydrogen, right? And then in hydrocarbon, the tertiary hydrogen occurs singly. So it's just one hydrogen standing, as we can see in this case. Very simple. Very simple. So we can be given compounds, just classify the hydrogens. They are compounds with only primary hydrogens, as has been illustrated here. This compound, the neopentane, has only primary hydrogens. Very simple. Very simple. Now, isomerism. Methane and propane are the only alkanes with molecular formula CH4, C2H6, and C3H8. Now we are saying that these 3 basic alkanes do not occur as isomers. They always occur as unbranched chains. However, the others, that is from carbon number 4 onwards, right? From carbon number 4 onwards, all form constitutional isomers. So if you have butane, right? Now, the unbranched one is what we call the N-butane or the normal butane, right? Now, the same formula can be for isobutane, that is 2-methyl propane. 2-methyl propane. So you realize that this one is branched. Now, these 2 compounds are called constitutional isomers because they differ by connectivity, right? They differ by connectivity. Good. So that is what we are talking about here. Now, if you have anything about 4 or more, you get isomers. So 4 will have 2. Now, if we have 5 carbons, it also has isomers. How to get the isomers is actually just change in trend. So I will try with the next one, not this one. So let's just go through how we get that of pentane. Good. So pentane, C5H12, right? Okay. Now we can get the normal pentane here, right? So N-pentane. Then we can have substitution on carbon 2. So then we get 2-methyl butane or isopentane. And the last one is that we can get 2,2-dimethyl propane. 2,2-dimethyl propane, right? 2,2-dimethyl propane. Good. That is new pentane. Now, all these are constitutional isomers. They are all constitutional isomers. Good. So an exercise has been given here. We are supposed to write for C6H14. Now let me use a white screen to show how I'll derive all my possible isomers. So the question I have here is C6H14. Good. Now I'll first start by drawing the normal one, the unbranched one. So I would have CH3, CH2, 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 CH3. So this is the unbranched one, right? 6 carbons, unbranched one. Then I will start branching. So I'll make, let's say I'll cut this one off. This one is N-hexane. I'll decide to cut this one off, and then I'll make a substitution occur here. So I'm using the same thing. I will have CH3, CH2, 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 CH3. Now, how many carbons do I have here? I've just drawn 5 carbons, right? Just 5. That means I have 1 extra carbon. Then I'll make a substituent here. If I'm putting a substituent here, it means I have to reduce the number of hydrogen here. So instead of 2, I would have 1. Then I'll have CH3 here. So this will be different from this one. This one right here will be different from this one, right? Now the name of this one will be 1, 2, 3, 4, 5. So pentane, it will be 2-methyl pentane. Right, now I can decide to shift this group here, right? If I shift it here, I'll have something like CH3, CH2, 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 CH3. Now I want to save this up 20. I'll bring the CH3 here. That means these 2 should go away. So I'll erase these 2. Right? Now this is what I would have. This is what I would have. Now this one is also different from the former one. This is different from this one. So this is 3-methyl pentane. So I'm just changing the arrangement, right? 3-methyl pentane. Now I cannot move this one here again, because if I move it, I'll get the 2-methyl pentane again. So I'll decide to go to dye substitution. I'll decide to do dye substitution instead. So dye substitution. Let me start the dye substitution. So then I would have CH3, CH2, CH2, CH3. Now this is how many carbons? This is 4 carbons, because I want to do dye substitution, right? Now the substitution, I'll make one occur here. So clean this, make one occur there. Clean this, make one occur there. So I'll have CH3, CH3. Now this compound is different from all that I've drawn so far. This one will be 2,3-dimethyl butane. Very simple, right? Now I can still change the arrangement of this dye substitution. I can make the 2 dye substitution occur on just 1 carbon atom. So I would have CH3, CH2, CH3. So this will be CH3 here substituted. This will be CH3 substituted. This one is different from the previous one. This is 2,2-dimethyl. 2,2-dimethyl butane. Right? Good. So you realize that I can just be switching, changing, and then getting new compound. Now, so far I've gotten 1, 2, 3, 4, 5. 5 different. And that is how you get your different isomers. You just be changing them. Now, once you are changing them, you get all your possible isomers intact. So these are the 5 that I derived, all of them here. You can try your hands on them. Next one, physical properties of alkanes. Now we are saying that a series of compounds in which each member differs from the next member by a constant unit is called homologous series. The members of a homologous series are called homologs. So, I mean, if you consider methane and ethane, so let's say methane, ethane, propane, right? Now, these compounds, each of them differ from the next one by methylene with that CH2 between this one and this one to so CH2. Now, this is the first one, this is the second one, this is the third one. You realize that between these compounds, there's a constant CH2, which equals 14.0, right? 14.0 or 14 point some other decimal. So you realize that there's a constant unit between the different members of the alkenes. Therefore, we say alkenes are homologous series. Same for alkenes, same for alkynes. They are all homologous series because we have a constant difference between them. Constant difference between them. And then each member will be a homolog, right? Good. Now, the physical property. We are seeing at room temperature, 25 degrees Celsius and 1 atmosphere pressure. From carbon 1 to carbon 4, which are unbranched, are gases. Then carbon 5 to carbon 17 are liquids. Then the unbranched carbon 18 or more are solids. Now, this is an information we have to keep. We are focusing on unbranched because branching would change a lot of properties in what we are talking about. So now we are focusing on the unbranched ones, right? These are the general rules that we have to keep in mind. Good. Now, the next thing here they have said here is that boiling point of unbranched alkene show a regular increase with increasing molecular weight. Now, the whole idea here is that alkenes have weak van der Waals force between them. Yes, and then that force is favored by yes, so it's favored by larger surface area and then larger molar mass or molecular weight. So as you are going, from carbon 1 to let's say carbon 20, right? Now what you are doing is that you are increasing the molar mass. You are also increasing the surface area. So you realize that gradually it will turn from being gases to what? To being solids, because now the carbons are increasing, then intermolecular force is becoming stronger. Above 18, above carbon 18 is strong enough to make it what? A solid at room temperature, right? Good. Now, boiling point will increase with increasing molecular weight because of the same reason, right? Because of the same reason. So increasing molecular weight. Increasing molecular weight would increase the van der Waals intermolecular force, right? That will increase the boiling point. Very simple. Now we know that branching will change a lot of properties, right? So the first thing we are saying that branching will lower the boiling point. Now we are talking about intermolecular force, which is favored by the molecular weight and then the surface area. Now, when branching increases, what it does is that it makes the structure look more compact. Now, when it looks very compact, right? If it looks very compact, it reduces the surface area for bonding. Now, once the surface area is reduced, the intermolecular force will reduce, and what? The boiling point what? Would also be lower. That means you require less heat what? To break the bonds or cause it to what? To boil. Very simple. So you realize that N-hexane, 2-methyl pentane, 3-methyl pentane, all of them, all these three have the same number of what? The same number of carbons. If you come, the last will also have the same number of carbons. So we cannot even talk about increasing molar mass. The difference here is that the branching has increased as we go. So this is mono branching, this is di branching, right? 2 branching. I realize that as branching increases, the boiling point will lower. And then that is simply because of lower intermolecular force, because of decreasing surface area, right, for bonding. Very simple. Very, very, very simple, right? Good. Then you realize that even between the two disubstitution and then the two monosubstitution, there's a difference a little bit. Now I realize that between the 2-methyl pentane and then the 3-methyl pentane, the 3-methyl pentane is having a higher boiling point because it is symmetrical. I mean, the substitution is directly in the middle. It's symmetrical and quite stable, right? That increases the boiling point. It's the same for this one. Because the two substitutions in the substitution of 2,2-dimethyl-butane are the same carbons, their effect can cancel. So this one is quite stable relative to this one, which has a substitution on different carbons, right? Good. So this one is because symmetric, that is the monosubstitution. 3-methyl pentane is symmetric, more stable, and higher boiling point. This one we are saying because the substitution occurs on the same carbon. Also occurs on the same carbon, their effect would roughly cancel out, and then make the thing quite stable, right? Good. So that is very simple. Now for melting, we are saying that there's an alteration in melting point of unbranched alkanes with even numbered carbon atom to the next one with odd numbered carbon atom. So if we are talking about melting point, then the order changes between the even and odd numbers, right? So if you take ethane, ethane is even, right? Now ethane has a higher melting point than propane. If you are familiar with negative numbers, you understand what I'm saying. This number is higher than this number, right? So you realize that ethane has higher than propane. You contain butane, and then so you realize that now the order is between even, odd, even, odd, even, odd, even, odd. That is how it works. That is how it works. So now the explanation too is very simple here. Now, if we talk about melting, consider something moving from the solid state to what? To the liquid state. Now, when we have our alkenes, right? When we have our alkenes in the solid state, they are arranged in something that we call crystal lattice, right? That's they would kick as crystals. They will just kick as crystals. And so now, if you are a solid which behave as a crystal, we have something that we call crystal lattice that are fixed position that you occupy. They are fixed position that you occupy. You have to arrange yourself in these positions so that you can bond with the neighboring molecule, right? That is what happens. Now, if you are even numbered, you can fit well into these crystal lattice. And so your bonding is enhanced because of proper arrangement, right? Now, if you are odd numbered, your arrangement is not really proper. Now, because of proper arrangement, improper arrangement for odd numbers, it will lead to poor what? It will lead to poor bonding. Now, poor bonding would what? Would lead to what? Lower melting point. So between ethane and what? Propane, that is what is happening here. That's because ethane is even numbered, it can arrange itself well within a crystal lattice, and then that will enhance the bonding, and then would have what? A higher melting point, right? Good. But then propane, because of the odd numbered carbon atom, the arrangement is not good. That will affect the extent of bonding, and then it will require lower energy or lower melting point to break it, right? Because it's less bonded. But then the order will change as we go along because let's say if you consider butane and pentane. Now, in as much as we are talking about arrangements, remember that the force holding them is van der Waals, and then when the number of carbons increase, right? When the number of carbon increases, it will change. So we realize that the order can go, but then up to where we have a lot of carbon atoms, you realize that the one that has a lot of carbon atoms might interfere with the odd and even number arrangement. But then for now, we are saying that the alternation is between odd and even number. In a normal day, we are expecting the even numbered ones to have higher melting point because they can arrange themselves better to enhance the level of bonding between the different molecules. Therefore, require higher energy to break them. That's higher melting point. Right? That is what we are talking about here. Very simple. So we are saying that branching producing highly symmetric structures results in unusually high melting points. Now, when branching occurs like this, right, it can produce unusually high melting points. So that is something that we have. So this compound here has melting point over 100, over 100, over 100. That is an high boiling point too, because the bonding between it is enhanced. It's enhanced. Next one, solubility. Now we are saying that alkanes and cycloalkanes are non-polar. So they cannot dissolve in water because water is a polar solvent. Very simple. Now they cannot form hydrogen bonds, so they cannot dissolve in water. Very simple. But then they can actually dissolve in non-polar solvent like benzene, right? Because they are non-polar, they can dissolve in non-polar solvents. Good. That's solvent of low polarity. Very simple. Now let's talk about conformations of alkanes. Conformations of alkanes. So we are saying conformations are the different spatial arrangements of a molecule resulting from the rotation of groups about single bonds. Now, when we have double or triple bonds, those bonds are rigid, right? So free rotation is restricted. But then if you have single bonds, the single bonds can freely rotate. Can freely rotate. Now, because of the rotation about single bonds, we can have different arrangement of spatial groups, right? Different spatial arrangement of molecules, right? Good. Now, these arrangements will affect the stability of the molecule. So we realize that a single molecule can assume different arrangements that will affect the stability of the same molecule, depending on what the arrangement it has assumed. That's a more reason why we have to study the different conformation the molecule can assume, right? So conformation is just a different spatial arrangement the molecule can assume. And then it can assume this movement because, or sorry, this arrangement because of what the free rotation around single bonds. Very simple. Now we are saying conformation analysis of ethane. Ethane have two distinct conformations. We have the staggered conformation and the eclipse conformation. These words are quite explanatory, self-explanatory, but then we have pictures to help us understand them. So staggered conformer means the two spatial groups. The spatial groups do not lie directly over each other, no, right? But then the eclipse one shows that the two conformations lie directly over each other. So this is eclipsed. The two hydrogens are lying exactly opposite each other. They are facing each other exactly. These ones are not facing each other exactly. Now, this is ethane drawn. Now, ethane is something like this. C, H, 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 H. Right, this is how we are, this is ethane, the structure of ethane. Now, if you are drawing it like this, that's in the conformer form. And you first draw, we assume the carbons are facing directly behind each other. So the two carbons, you can't see them. That's this one and this one. If you stand here, you might not be able to see this carbon again. So we don't show the carbon, right? Then the three hydrogens around it can be drawn like this. So this is hydrogen, this is hydrogen, this is hydrogen. Now, if you want to draw the hydrogens at the carbon, which is at the back that you can't see, you just draw a circle. So you draw a circle like this, right? Now, then you bring that one there. So hydrogens, hydrogen. So this is a hydrogen. This will be a hydrogen. This will be a hydrogen. Now, the lines touching the circle belongs to these hydrogen belongs to the carbon at the back, right? And then the one here is the carbon, which is just facing us. Now, this is how we do a staggered conformation. Now, if I want to draw an eclipse conformation, it's like this. So this is the carbon near me. The three hydrogens suspended is here. Then I can draw my circle. So now I want to draw eclipse. So this one is eclipse. This is eclipse, right? So I can just bring my hydrogen. That's 15. Now it can change, right? When we get to butane too, I would explain to you so that you know. Right? But then this is how we draw ethane, and these are the two possible conformations it can assume, right? It can assume the staggered conformation, and it can also assume the eclipse conformation. Very simple. Very simple. Good. Now we are saying the staggered conformation has the lowest energy and hence the most stable, right? And the eclipse conformation has the highest energy and hence the least stable. Now, when the energy increases, it decreases the stability. So that's what we are establishing here. The staggered is the most stable, eclipse is the least stable. Now, we are seeing that each CCH bond, that's each CH unit in the ethane is characterized by a torsional angle or dihedral angle. So pictures has been used to illustrate it. Now we have hydrogen as against hydrogen here. Now the two hydrogens are facing each other directly, right? The two hydrogens are facing each other directly here. So the torsional angle here is 0, right? Good. Now this is a staggered conformation. This is an eclipse, this is a staggered conformation. This is also another staggered conformation, right? I mean, the staggered conformation, if the groups of interest are 60 degrees apart, we call them gauge, right? And then if it's directly opposite, we call it what? Anti-conformer. We call it anti. So the two here are both staggered, right? Good. Now you realize that depending on the angle between them, the smaller the angle, the higher the energy. And the higher the energy, the less stable you are. So the torsional angle here would give us a measure of what's the stability of the group. Now, it will give us the measure of the stability, right, of the group. Now, the destabilization, that will arise because of what? This torsional angle, or because of this bond line directly over this one is what we call what? The torsional strain. The torsional strain. So you realize that this hydrogen would repel this hydrogen. Now that repulsion will bring some destabilization. The destabilization that will arise because of this eclipse is what we call what? It's what we call the torsional strain. It doesn't only occur here, right? Even here, there will be some level of what repulsion between this hydrogen and this hydrogen. It will not be as much as this one. So you realize that this is quite stable relative to this one. But then the destabilization that occurs because of the repulsion between these two, right? It's what we call the torsional strain. The same thing will occur here, but then it will be the lowest here because these groups are what? Are directly opposite. So this one will be the most stable because it would have what? The least torsional strain. The least torsional strain. Right? So the destabilization that will arise because of what? Because of the eclipsing, or because of the repulsion between the hanging groups or the spatial groups. It's what we call what? The torsional strain. Now keep note of these terms: dihedral angles, torsional strain. They are all examinable. Now, if we talk about steric hindrance or steric strain, then we are talking about the total strain. So the torsional string, we are just considering the two groups. Remember, these groups, as they are repelling, these groups are also repelling, these groups are also repelling. So if we sum all the strains, the total of all the strains of the spatially dependent features, then we get what? The steric strain. Then we get the steric strain. Very simple. Very simple. Good. Now, these are different conformations, but this is of butane. Butane, the last one we're doing, we're focusing on ethane. So let's see how we'll draw butane. Let me share my screen and then draw butane. So this is butane. C, 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 C. All right. This is CH3. This is CH3. Now this is CH2. This is CH2. Now we will draw it such that this will face each other. So these two will face each other, right? Such that these two will face each other. So you would not see this carbon, you would not also see this carbon, right? But then these carbons would be hanging. So these would be the spatially dependent feature. So I'll start by indicating this carbon, this one, with this dot here. Then, so you realize that this carbon here is attached to three things. Let me open it up for you to understand. Yeah, so this carbon here, we attach one hydrogen down here. So I'm focusing on this carbon, and that's what I have here, right? Good. Now I have one hydrogen here, and the last feature here is CH3, right? Good. Now, if I'm supposed to focus on this carbon, let me draw it again. It's a different ink. So this is H, this is H. Now this the carbon, right? Now, for me to show this one, it will be directly behind this one, so I can't see it, but then I'll use a circle to show it. So this is it, right? Good. Now, assuming I'm drawing gouge, then the three groups which are attached to that carbon. So we realize that we have three other groups. It's attached to this one, of course, right? But then you have three other groups focusing here. So I can have the hydrogen here, and then the CH3 here, right? So that is how I draw my butane. This is for butane. This is for butane. This is how you draw your butane. You realize that if you are drawing it like this, then you can have three different arrangements. You can draw it as I have drawn here, right? But now I realize that between this and this, you have something like 60 degrees, okay, between the two. Now, if we have butane, then the most important proportion we are talking about are between the methyl groups, right? Methyl groups. So that's what we are focusing on. So these groups are 60 degrees away from each other. Now, the same staggered conformation, we can draw it like this. So this is gouge, right? This is a gouge conformer. We can draw it like this. So a circle here. So this is the first carbon, right? H, CH3. Then our circle will come. Then same staggered conformer, right? So then I would have CH3. Now, because the groups in focus, right, that's the CH3 here and the CH3 are directly opposite. Even though it's staggered, it is an anti-conformer because the degree between these two are 180 degrees. From here to here is 180 degrees, right? So this is anti-conformer. The last way we can draw this is the eclipse conformation. That is, so for that one, I would have this dots coming here, coming here, coming here. So there are three groups, H here, CH3 here, right? Then I would have my circle nicely drawn. Now it's eclipse, so it's close. So one here, no, not there. I have to be very artistic. So then one here, the last one is here, right? So this is can have H here, then CH3 here. So this is eclipsed, right? This is eclipsed. This is eclipsed. Hey, so eclipse, sorry, my spelling of eclipse is messed up. Forgive me. So eclipsed. So sorry. But the eclipse can also be drawn in a different way, because now we have drawn eclipse so that the CH3 can meet. It can still be eclipse, but then it would be that the CH3 and then the H is meeting. So let me draw my last eclipse here. Good. So this can be H, CH3, and my circle here. So it's eclipse. So right. So this can be CH3, and this can be H, and this can be H. Right. So this is an eclipse conformer. This is an eclipse conformer. And I realized that this eclipse, the two groups that we are talking about here are like 120 degrees apart. They are 120 degrees apart. So you realize even though it's eclipse, it's different from this one, right? So that is what we have there. That is what we have on the slide. Let's go back to the slide and then explain what was happening there. So this is an anti-conformer. The two groups we have focus for butane are directly opposite each other. There's an eclipse conformer, but there's an eclipse between the CH3 and the H. Then we have a gouge that's 60 degrees from each other. Then we have an eclipse where the two groups of focus are directly on top of each other. It's another gouge. So you realize that the I is the same as what? The V. Then we have the last eclipse, right? Now this eclipse is also the same as something. It's also the same as the I. So let me connect them for us to have a better understanding. This one is the same as this one, right? But they are the same. And then this one is also the same as this one, right? They are the same. That means we have 1, 2, 3, 4. So we have actually 4 different arrangements, not 5. We have 4 different arrangements. We have 2 staggered and 2 eclipsed, right? Now there are questions down there that we have to answer. Let's go there and see the questions. The first one is, which conformer is the most stable? Now the most stable is always staggered, right? But then which of the staggered is most stable? It is the anti, because the anti has the least proportion because the groups are 180 to each other. So the anti is the most stable. And then which one is the least stable? The least stable is eclipse. But which of the eclipse is the least stable? The eclipse, which is the least stable, is so the 2 eclipse. We have this eclipse, and then we have so this eclipse is between hydrogen and then the methyl group. It's not really very stable. The least stable one is the one that we have the 2 methyl groups that are really facing each other. This one will have the highest proportion, right? Good. So even though it's eclipse, but then it's the IV, which is the least stable. The IV is the least stable. So that is that for that. We are done. We are done. Now, chemical reactions of alkene. I've already mentioned that the reaction, common reaction, that is one that goes addition reaction, but that is not the only reaction, right? So we are seeing alkenes are generally inert to many chemical agents. Example is paraffin. That is why we store metals under paraffin, because they are not reactive, right? They are not very reactive. Good. So that is that for that. Now they are unaffected by acids and bases, right? Good. But then you can burn alkenes. Now, when you burn alkenes, you are getting carbon dioxide and water, right? In actual fact, if you burn every hydrocarbon, whether alkene, alkene, or alkyne, right? Every hydrocarbon, when you burn it completely, right, in excess oxygen, you are getting what? Carbon dioxide and water. So this is something you have to keep in your head. When you burn hydrocarbons, you get carbon dioxide and what? Water. Very simple. So simple. Right? So this is alkene burning. So we react with oxygen to yield what? Carbon dioxide, water. Now, burning of fossils or organic compound is called combustion. So technically, we say it is combustion, right? Good. Now, chemical reactions of alkenes. So the next reaction we have to focus on, apart from combustion, is the free radical chain reaction. So we see alkene can react with chlorine or bromine when heated, and then explosively with fluorine. Now, generally, we are talking about reactions of alkenes with halogens. Now, these are two extremes that you have to look at. That the halogens, we have fluorine, chlorine, bromine, iodine, astatine. Astatine does not really behave like the other ones, so you hardly see them undergoing typical halogenic reactions, right? Good. Fluorine is very reactive, so highly reactive, sometimes can lead to boiled and all, and then sometimes it can lead to violent reactions. So that is what we can see here. It said it reacts explosively with fluorine, so we hardly even use it. But we have other ways of curbing this, right? So the most common one, and then iodine is very unreactive. Iodine is very unreactive. So on a normal day, we don't use the extremes. You would hardly see we using fluorine, hardly see we using iodine because it's less reactive, because sometimes some of these reagents need special attention. The ones which are moderately reactive and then we use most of the time to be chlorine and what's bromine, right? Because they can give higher yield and then they can be controlled relatively. So that is the ones that we use. So in this case, for our free radical, mostly we are using just chlorine or bromine, right? Now let's look at what happens. If we have methane plus chlorine in the presence of high heat, 400 to 440 degrees, or sometimes we say UV or HV, high energy, right? Now you get chloromethane. What's happening here is that there has been an addition reaction, a substitution reaction. So one hydrogen has been taken away, and then it has been added to this compound. And one chlorine has also been taken away and been added here. That's what we have. We have chloromethane, and we have chloromethane and hydrogen chloride, right? Good. Now that chloromethane can also react with chlorine. It reacts with chlorine to give you dichloromethane. So it's the same thing that is happening. It's the same thing that's happening. We lose one of the hydrogens here, and then we'll add one chlorine here. The hydrogen will come here and form the hydrogen chloride, and then we'll have dichloromethane. Then the dichloromethane can also go into reaction. So we lose one of the hydrogens here, and then we bring one of the chlorines, the trichloromethane. The trichloromethane can also go into reaction, right, to get me tetrachloromethane and then the hydrogen chloride. So that's what will happen. Now, when you get to the tetrachloromethane, you cannot react with more chlorine because it has no hydrogen. Remember, hydrogen is the functional group of alkenes. So you need the hydrogen before it can what? It can react. It's the hydrogen which is responsible for the reactivity of the methane or of the alkene. So once there's no hydrogen, it cannot react. And so if you see something like CCl4 plus Cl, this one is no reaction because there's no hydrogen attached here. This is a trick that you might encounter easily. Then it's a bonus question when you see it. Very simple. Good. Now, how does this reaction occur? The reaction occurs basically in 4 steps, right? There's actually 3 steps. The last step is just termination step. So the first step is the initial or initiation step. Now, the initiation step involves the breaking of what? The chlorine molecule into a radical. Now, this one requires energy. That's why you need the heat or the high energy radiation, right? So that it can break it. Now, the type of cleavage that occurs here is what we call homolytic fission. Homolytic fission. Reaction can be fusion or fission reaction. This one is homolytic. Homo means same, right? Homolytic fission. So there is homolytic fission to produce equal radicals. So Cl2 will break homolytic fission. Now we'll have two of the same radicals. So this is what we call homolytic fission, right? Now, if we are representing homolytic fission, we use a half arrow to represent it. So it is chlorine against chlorine. Now, these ones are in a covalent bond, right? They are sharing this lone pair of electrons. When the fission occurs, one electron will go here, and then another electron will go here. We use half arrows. Take note of that. We use half arrows, and that will get us our radical. Two sets of equal radical homolytic fission. Very simple. So after generating our radical, then our radical can attack the methane. Right? Our radical can attack the methane. Now, when it attacks the methane, it attacks it such that it will produce a radical out of the methane. So we have meta radical. So this is what will happen. Now, the chlorine is a radical like this. There's this methane. This is CH3. I'm just separating one of the hydrogens so that you can react it with, because there's one hydrogen at a time. We take one hydrogen at a time. Now this line here is the bond, the covalent bond. It also represents two electrons, so that's two dots. So let me put the two dots there. One dot here, one dot here. Now what will happen here is that this hydrogen will move as a radical. So the whole hydrogen will move, homolytic fission, one arrow, right? And then it will join this one arrow like this. So then that will form the hydrogen chloride. And then there's another homolytic fission here, so this one will break onto this. So then I'll have plus my CH3 radical. This is the mechanism of action. Now this meta radical will attack a molecular chlorine. So now I have my meta radical here, right? Then I'll have my chlorine. It's chlorine molecule. So then this molecule will be contributed, this radical will be contributed. Now this chlorine will move here as a radical. There was just one electron, and then this one can break onto this. So then you would have CH3Cl as a normal compound plus the Cl dots. Now this radical can attack another methane or even this one, right? It can attack this one. That's if you are continuing. Can attack this one. So then I would have something like this. CH2Cl. Then I'm just separating this hydrogen so that I can do the reaction. I have a radical here, right? Let me bring my electrons. So one electron here, one electron here. Now this hydrogen, the whole of this hydrogen will move. It will move. Always arrows will move, show the movement of electron. It will move as a single electron, a radical, right? Then this one will also move. Half arrow, then it will meet. Then this electron will also break onto this carbon, half arrow as a radical. So you have this radical, CH2Cl dots. The dots is on the carbon plus hydrogen chloride, right? And this radical will attack another molecular chlorine. So attack another molecular chlorine. So that is how the mechanism proceeds. It goes on and on and on and on and on and on. Then I'll produce another radical. So then from this reaction, from this one, I would have CH2Cl2 class Cl dots, right? And then this Cl dots can actually continue, right? So always I'm producing a radical, and then that radical can. So the reaction, that's what we call it, a chain reaction, right? That's what we call it, a chain reaction, because while the reaction proceeds, we produce more radicals, which will continue the reaction, right? Now it will react until we have all the CH removed so that we form CCl4, right? That can be a termination step. Because we don't have any hydrogen here again, the reaction cannot continue again. The next thing that can terminate the reaction, that's the CH4, is when you have two radicals meeting. The two radicals meeting can be this. It can be Cl dot plus another Cl dot. Now, when the two Cl radicals meet, it can terminate, it will form Cl2, right? When a radical like this also meets a radical like this. Now that can also terminate the reaction. Now when this radical meets a radical like this, it can also terminate because when these reactions occur, they don't produce more radicals. So whenever two radicals meet in the chain reaction, then it will terminate the reaction. So these are the termination. They can ask us to state maybe two scenarios of termination. Then we can just combine any of these two radicals to be our termination step, right? Good. So that's for the whole mechanism. We have the initiation where we produce the radical. Then we have the chain propagation where the first radical will produce more radical, right? Then that's methyl radical will continue reacting. So react with molecular chlorine as a step 3. Then it will continue like that. Continue like that. That is all till we get to the termination step where the reaction should stop because two radicals have met. That's for that. Now, the next thing, synthesis of alkane and cycloalkanes. So how we can make them. Now, the first thing we are talking about here is hydrogenation of alkenes and alkynes. So alkenes and alkynes are unsaturated in the presence of excess hydrogen gas and then platinum catalyst or palladium catalyst or nickel catalyst, the metal catalyst, right? We can break that unsaturation, that's those pi bonds, and then form saturated compounds, which are alkenes. So, example, we have propane here, right? In the presence of nickel and then the hydrogen gas, we can break the double bond to single bond. Then we have what the propane, so propane to propane. Right, that is what has been shown here. Now this is cyclohexene, and then the presence of what? Of the hydrogen and then the metal catalyst, we have been able to form cyclohexene. Now I think it is worth putting across at this point that if you have just one double bond, you require 1 mole of hydrogen gas to break it. If you have one triple bond, you require 2 moles of hydrogen gas to break it. Very simple, so that this can help us in balancing our reactions. Very simple. The next way of producing alkene is a reduction of alkyl halides. Now that reaction is actually a substitution reaction. So what happens is that we have an alkyl halide that's an alkene connected to a halogen, right? Now what we do is that we replace the halogen here or substitute the halogen with the hydrogen, right? And then the condition you need is zinc. Now this is very specific. We are not saying any, we are saying zinc and what? An aqueous acid. So let's say we have zinc and then ethyl. Now that aqueous acid, the halogen of that acid should correspond to the halogen in the alkyl halide. An example is what we have here. Now the halogen here is bromine. The acid we are using is what? Is HBr. So the bromine here, then we have the zinc metal. Now the reagent will displace the bromine and then put the hydrogen there to get our normal butane. Very simple. Another one is this one too. Same conditions met, then we produce alkene. Now what you have to keep here are the conditions of the reaction, because we can give you chemical reaction, we can give you the reactants and then the condition and ask you to produce products. You should know that if you are given these reactants, that's like aqueous acid and zinc, then most probably you are forming alkene by reducing the alkyl halide. Very simple. So take note of the reagents. Now, the last way of synthesizing alkyne is by alkylating terminal alkynes before you break the unsaturation to make them saturated. Very simple. Now, we are saying that this can only be done on terminal alkynes. There's something about terminal alkynes that make this alkylation possible. Let's read what has been written. Now we are saying that the acetylenic hydrogen is weakly acidic. That's the pK is approximately 25 and can be removed by a strong base, example sodamide, to give an anion called alkynide anion or acetylenic ion. Alkylation of the acetylenic ion and subsequent hydrogenation produce alkenes. Now let me demonstrate this before I come back to the slide. So let's share a white screen. Good. Now, so let's take terminal alkyne. CH3, C, triple bond, CH. Now, we say terminal when the triple bond is close to a carbon or is on a carbon which just bears hydrogen, right? So this is the terminal alkyne. It's a terminal alkyne just because of this part, the CH part, triple bond CH. So terminal alkyne is like this, right? With maybe CR. So this is a terminal alkyne. This group can be a long chain. It can be a long chain, can be a long alkyl group or any other group, right? Yes. But then this part is what we call the terminal alkyne. So this, what I've drawn here is a terminal alkyne. This is not a terminal alkyne. This is not a terminal alkyne because you cannot have this triple bond CH group. You don't have this triple bond CH group, so it's not a terminal alkyne. So this is not, but this is a terminal alkyne. Now we are saying this bond is very strong. This bond is very strong. It's an sp bond. Sp bond is a very short bond and a very strong bond, right? So it has made this bond quite polar, and then there's a little bit of acidity illustrated by this. Now, because it is weakly acidic here, if you have a very strong base, you can deprotonate this one. That is the whole idea we are talking about. You can deprotonate it. That's acid-base reaction. Because it's an acid, it can lose this hydrogen as a proton. Now, when you lose as a proton, it will be an avenue for us to what? For us to introduce an alkyl group to make it longer. So that is the whole idea we want to communicate here. That's the whole idea. So let me draw my, okay, this is my terminal alkyne. Good. Now this is acidic. How can I get rid of this? I'll use a strong base as sodamide. Now the sodamide in solution, the important thing that we'll use is this one, NH2 ion, because the sodium and then the amine group here will dissociate, right? So the Na. Now, what will happen here is that, let me expand it a little bit. So what will happen here is that good. Now, so this base, this strong base, we use the lone pairs here. Now, always arrows move from electrons to atoms. So, because the arrows show where the atoms are moving. So the lone pairs here will be used to extract this hydrogen. Now, these electrons will be deposited here because this one is taken as a proton, H plus, right? So I would have something like this, CH3, C triple bond, C, then the electrons are deposited here, plus NH3. NH3 without any negative again because I've taken one hydrogen onto myself. So I would have ammonia as a byproduct. Now, this is the intermediate you'd get if you add the strong base to the terminal alkyne. Now, the next thing that we need, the next reagent that we need is an alkyl halide. It's an alkyl halide. So let's say my alkyl halide can be CH3Cl. Now, this CH3Cl, what will happen here is that this lone pair, see, always the halogen here is more electronegative than this carbon. So it will induce some level of positivity in this carbon slight one, very slight one, right? And then the carbon here would be, the chlorine here will be partially negative, right? Now, because the electrons are deposited on this carbon is highly unstable. It's highly unstable, and then it will go and attack this positively charged carbon, right? Now, when it attacks it, the bond between this carbon and chlorine will also break onto the chlorine. We call chlorine a good living group because upon attack, it can live on its own. So what I will have here is, I would have CH3, C triple bond, C, CH3, plus the Cl minus. Now I have successfully alkylated my terminal alkyne. I started from here. I have successfully alkylated my terminal alkyne. Right? Now from here, if I want to produce my alkane, then what will I do? I have to add excess H2. So so excess H2 gas in the presence of platinum or palladium catalyst. Then I'll have my CH3, CH2, CH2, CH3. Remember, I need 2 moles of hydrogen to do this reaction, right? So I'll break this. I'll break the 2 bond here. I'll have CH2 here. This place will be CH2. This place will be CH2. Very simple. Let me work with another example here. So I can have an example like this. So CH3, CH2, C triple bond CH. So this is my terminal alkyne. And my alkyl halide can be CH3, CH2, Br, right? And then my A will be sodamide. I'll have my sodamide here. Then I have my excess hydrogen, and then I have my platinum. So how would I show the mechanism of this reaction? The overall reaction is that, I mean, you can use your eye to tell. The overall reaction will be that CH3, CH2, C triple bond CH2 plus CH3, CH2, Br in the presence of sodamide, sodium imide, and then hydrogen in the presence of platinum. Now, if this is what I'm doing, what will happen here is that this carbon that is directly bonded to the bromine, the carbon which is directly bonded to the bromine will connect with this carbon, the one that is terminal. So what I would have here, that is what I'm supposed to have. If I connect this one is CH3, CH2, C triple bond C, CH2, CH3. Now make sure you bring the CH2 before the CH3 because it is where the bromine is attached. That is the same carbon that will be attached to this carbon. There will be a direct connection. Then you just repeat what continues it or what follows it, right? Very simple. Now, this could have been my answer if I didn't have my excess hydrogen and platinum there. But because I have my excess hydrogen and platinum, it means the triple bond will be broken. So my final answer will be CH3, CH2, now CH2 again, CH2 again. That is these ones broken, right? And then CH2, and then CH3. So this will be my final answer. This will be my final answer, right? We can work more on the overall reaction. Let me cite another example on the overall, just writing the overall reaction. So CH3, CH2, C triple bond CH. Good, plus, let's say CH3, 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 Br. So this is it. Now the conditions are just sodium imide. Now in this case, there's no excess hydrogen, right? Sodium imide. Now what will happen here is that where this Bi is bonded, this carbon will connect to this carbon where we have the terminal alkyne. So this hydrogen will move away. So what I will have is I would have CH3, CH2, C triple bond C connected to this carbon. So I'll write this carbon. And then whatever is around this carbon, I'll just repeat it. So it has 3 bonds around it. CH3, CH3, CH3. Very simple. I'm done. Now, this is my final answer because there's no platinum and hydrogen here, so I'll maintain my triple bond. But then, if I'm supposed to add hydrogen gas in the presence of platinum or palladium catalyst, then it means I'm breaking these triple bonds. So I'd have CH3, CH2, 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 then CH3, CH3, CH3. Very simple. So this is everything, right? Now the last thing we have to try, let's try the mechanism, right? So let's try the mechanism to arrive at the answer. You can look at the reactants to predict your answer. You can also go to the mechanism to predict your answer. So let's use the mechanism to get our answer. So my example will be this one. So this is my alkyne. This is propyne. Propyne. Good. Plus, let's see, CH3, CH2. Yeah. Good. Now I'm doing mechanism, right? Good. Now the first thing that will occur, so let me just underline this and then draw my mechanism here. First thing that will occur is the attack of what? Of the good. So dash H. So the sodamide here, what is important to me is the imine part of the sodamide, right? The imine part of the sodamide, negative. Now that one would attack this hydrogen. When you attack this hydrogen, this bond will break here onto this. So then I will have CH3, C triple bond C. Then the electrons are deposited with a negative sign because electrons are negative, right? Plus ammonia. That's the first thing. Very simple. The next thing is that because the carbon doesn't want to contain electrons, it will make it very unstable. So it would want to give it to something. Now the bond between this and this is polar. The bond between the CH3, CH2, right, Br. This is polar. This is partially positive. This is partially negative. This is partially negative. And so what will happen is that this negatively charged species will attack this carbon. Very important, not the hydrogen, the carbon, right? Good. Then this bromine will break off, a good living group, so it will break off on its own. So what I would have here is a direct connection between this carbon and then this carbon. So I'll repeat everything here. I will have CH3, C, triple bond C, CH2, CH3. And if I want to produce my alkane, I would add my excess hydrogen in the presence of platinum, right, or palladium or nickel to get CH3, CH2, 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 CH3. Very simple. So that's it. That's it. That's for that. Let's go back to our slides and then look at what we have. Good. So that is what has been illustrated here. Very simple. Reaction with the sodamide would extract the acidic hydrogen here. The reaction with the alkyl halide, introduce the alkyl group there. In order to get our alkane, we have to add excess hydrogen in the presence of platinum. Right. Now the alkyl halide used must be primary and branched at its beta carbon. Now this rule is very important because it's showing us that not every alkyl halide can be used. Right. Good. So they are like the primary, the alkyl halide must be primary and unbranched at the beta carbon. So I'm sure we'll get examples that would show us all these, right? Good. So you meet example, I'll tell you it's not possible. There's one exercise here like that. So we just know. Now, the next one, they are like secondary and tertiary or primary, with beta carbon branching predominantly undergoes elimination reaction. All right, so, but then to do an illustration to just explain what is here, we are saying that, assuming we have a compound like this, so CH3, CH2, CH2Br. Now this alkyl halide, the carbon here is directly bonded to the bromine here. So this is the alpha carbon. This is the beta, this is the gamma, it goes on and on like that, right? Now we are saying that the alkyl halide we use should not have any branch on this beta, right? Because if it has a branch on the beta, it would undergo elimination reaction. So that what we are saying in here is that for the same thing here, for the same compound here, if we have something like CH3, CH2Br, so we have C3 here. Now, in this case, you realize that this is the alpha, still alpha carbon. This is the beta. Sorry, alpha. This is the beta. This would be the gamma. That's the longest chain. You can make the longest chain come down. But then you would have a substitution here on the beta. Now, when the substitution here on the beta, what will happen here is that this Br will go away, a good living group, of course. But then this group also, the beta will also lose a hydrogen. The beta will also lose a hydrogen for what? A double bond to be formed. So instead of we having the replacement reaction as we are saying, we'll have an elimination reaction instead. And that is what we don't want. So we are saying don't use an alkyl halide with a branch, right? Or a substituent at the beta position. Very simple. I've shown you the beta position where the carbon and where the halogen is attached. That carbon is the alpha. The next one to it is the beta. You make sure there's no substitution there, else you undergo what's elimination reaction. Good. So that is that for that's very simple. Now, the last slide has questions for us, and very simple question. We will solve all of them here. Now we are saying choose an appropriate terminal alkyne for the synthesis of the following alkanes exercise. So now we have been given terminal and we have been given the alkanes. Now we are supposed to choose a terminal alkyne that can be used to synthesize this alkane. That means in effect, they have given us the product and they want us to get the reactants, because what we have been learning is that we get a terminal alkyne first. That is what we have been learning. We get a terminal alkyne. Then we can alkylate the terminal alkyne. After alkylating the terminal alkyne, we can use excess hydrogen and platinum to break it down. But then now they are not telling us this. They are telling us that we have been given the alkynes that we want, the alkanes that we want. We should find a terminal alkyne that can be used to synthesize this one. Now, the best way to do this is you find the longest end, the longest free end. So in this compound is like this, 1, 2, 3, this one, right? Then you just take the methyl group here and form the, alkyl halide out of it. So I'll take this, I'll cut this part off, the CH3. So my alkyl halide here will be CH3Br. And then after that, I will form my terminal alkyne between the next two carbons. So then I would have, so I'm repeating everything on. This part is untouched. Then this carbon, triple bond, carbon, hydrogen. So I've used these two carbons to form my triple bond. Now this will be my terminal alkyne. This will be my terminal alkyne. This will be what? My alkyl halide. And then always I would need a sodamide to do it. So that is that for the first question. Very simple. Now the next one, the brackets here are points of substitution. If you don't draw it, well, you get it wrong. So let's draw it again. Now we have CH3, CH, on top of CH is CH3. That is the one in the bracket here. And another half, I have another CH. On top of it is CH3. That is the one I have in this bracket. Then I have CH2, CH3. So as I said, I'll look at the longest free end. Which one is the longest free end? This is the longest free end. The side here is the longest free end. So the 2 here. Because if I consider this end, no, this is not free, there's substitution here. So what I will do is that I will take this one and use it as my alkyl halide. So I'll have CH3Br or CH3Cl. Then I'll try and form my alkynes using the last 2 here, right? So I would have CH3, C, CH3, H, then CH. Sorry, I will not bring this H again. Now I can eliminate the hydrogens like that, but I can't just eliminate a group like methyl group. So my CH is there. So then there's C here, there's this methyl group here. Now triple bond 1, 2, 3, C, H. So I'm trying to form a triple bond between this carbon and this carbon. But then because this carbon has a substituent already, you realize that if I introduce a triple bond, I have 5 bonds, but carbon form only 4 bonds. So it means this one is wrong. And that is the only longest free end I have. Now, if that happens, it means for this alkane, you cannot use the terminal alkyne approach to synthesize it. You can't. So this one is not possible. The second one is not possible. And the third one too, this one has been drawn well already. What is the longest free end? This part is the longest free end. You take this part as your alkyl halide. So the CH3, the R is here. You try and form your terminal alkyne from here. So CH3, 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 then here. So then I'll have C. The CH3 should come. But then if I try and draw my triple bond between this last 2 here, you realize that it wouldn't work because this one has a substitution. So if I draw, I make this carbon get 5 bonds, which is not possible. So this is not possible. So the last 2 are not possible. It's only this one which is possible, right? Good. So that's it. That's for that. And that will be all for alkanes and cycloalkanes. Other materials be made on alkanes, alkynes, and imines, right? Good. As I always say, if you have any questions, see any member of the academic board. And yes, if you want any private attention or private tuition, there's this number that you can call, and then we link you up with someone who can do. That one is as a fee, right? And the number is 024 2035222. So this is the number you can call, and then you'd have your own private attention or your private tutor, right? It's an agency. We call it the Intrepid Solutions. Intrepid Solutions, right? Good. And then this is the logo. This is the logo of Intrepid Solutions. So if you see it anywhere, solution, learning, a whole learning platform, right? So that will be all. I wish you all the best.